still not sure. Okay, I said recorded now. So let's begin. So let me first motivate the topic of memory hierarchy. Right now that we are back from our midterm, 1 week, not a break, but no class. We're gonna go through the midterm questions whenever I'm done grading, so I know what are all the mistakes that you have done, so that I can cover that. But if you think about one of the components that we skipped so far, we somehow say, hey, black magic memory is free, right? So let's keep that assumption. Let's keep that black magic up, right? From the programmer view, what do you want to see from the main memory? Programmer want to see the abstraction of the memory, right? Magical blob that are unlimited, contiguous. I can control whatever inside that continuous chunk, all right? I allocate the array from 1 to 1 million. I want to make sure the first element is next to the second element, next to the third element, next to every single thing is next to each other. Imagine in a real system, you buy DRAM, right? To put in your motherboard. How many programs do you have running at the same time? Hundreds, tens, at least 10 or more, right? You have the OS. The OS has many processes that one of them would be dealing with the display, the other one dealing with input and output from your keyboard, the speaker. There's also the driver that control the GPU. There's also like the other piece of software that monitor your system. There's also Word, Microsoft Word that maybe you open up to type the answer for your assignments. Chrome that maybe you're watching YouTube on another monitor so that you don't get bored to death when doing assignments, right? These are normal usage. Imagine those programs that want to use the memory. Allocation, deallocation, again, go back to my talk, right? About that GPU allocation that have blocks that are contiguous, but now you have multiple applications, so it's not as contiguous as much. So if you don't have this abstraction, how can I guarantee that my array that is millions entry is next to each other? How can I guarantee that there's nothing in the middle from the other program, right? That are literally using the physical DRAM, but it's somehow in the middle. Virtual memory would give you this notion. When you program, you never have to think about, hey, what's gonna happen if someone use the range of address inside this array that I allocate? All right. Programmer sees the virtual memory. Basically, every single piece of data that you have seen in Python, Java, C, and any language, including assembly, these are virtual memory. And the OS, as well as the hardware, would work together to give this illusion of this contiguity, as well as this basically unlimited space, right? So inside the hardware, the main memory, again, is a physical thing. It's a physical thing, right? So don't forget about that. We'll come back to these concepts when we talk about the main memory. Then the other thing that we want, again, black magic, right? Fast memory. So what we want from the main memories are things like this. Magically fast, zero latency. Somehow I issue the load, it arrives the next cycle, right? Magic. Unlimited capacity. No cost, right? I want to go to a computer store. It's like, hey, I want memory. They give it to me for free. Or at least it costs like, I don't know, 10 baht, right? I'm sorry, baht is like the Thailand currency. It's like $1. And that's impossible, right? Also, you want unlimited bandwidth. When I said unlimited bandwidth in the memory sense, what it really mean is think about the pipeline and the load store unit, right? Going back to lecture 7, we have the load store queue. Everything in that queue are pending load and store. I'm still processing my data. So let's say there are multiple things in there. It means you're basically issuing parallel memory access. And DRAM is basically designed to give you this parallelism. You can actually service multiple requests at the same time. There are some constraints we'll learn. We'll learn about this constraint not next week, but the week after. We'll talk more about DRAM. But these are the goals. But the goal is conflicting, right? First of all, if you want fast memory, it's likely not to be free. right? If you want unlimited, well, large memory, it's also gonna take longer to access. Imagine that, right? If I want to search for where is my data in the big auditorium, it probably take more time than one classroom, right? Because there are more people, more addresses that you have to go to. Fast memory is also expensive. Parallel access is also expensive. Why are these expenses? Think about SRAM and DRAM. So SRAM and DRAM these days are kind of like primary elements that you can use to store data. There are more, but these are the most major part that play roles in the program performance. So this is what you have to care about, basically. And also newer technology that are introduced to kind of like back up DRAM again, right? But uh, these are still kind of like on the shelf kind of thing, right? I've seen you review the processing in memory paper, like the Google workload paper, right? So you might say that, hey, this thing is possible, right? And yes, it's still in research, right? And I want to go sidetrack a bit, right? The review you've seen so far, including the paper that I collaborate with my colleagues, right? The Google paper, you have seen that these are actually research. These are frontier. Like it's totally new. So I want to highlight this because at TGGS, a lot of people confuse what the heck are research, including lecturers. I want to make sure you understand what are engineering and what are research. Engineering is I know the solution. I am a great engineer. I can hack things into this solution that would solve my problem. And that's awesome, right? It's awesome. It definitely has value. But when you talk about research, you also have to talk about the new elements. What's novel in the paper? And that goes into your review too. Like I like the summary in a sense that you seem excited every time you see new ideas, right? That hey, this is interesting, right? This is how you get performance. So that's when I said frontier research. Like it's a lot of unknown and a lot of depression because we don't know the solution. But you basically put together how do we enable new idea through novelty, right? So coming back to our topic, we have the main memory in DRAM and SRAM. We want, we are greedy. We want everything. We want to be fast. We want it to be big, right? You notice SRAM is faster. If you're not familiar with SRAM, basically they are 6 transistor, right? 4 for storage and 2 for accesses. Basically, 4 of them will be used as a cross couple inverter. So basically, it's going to look something like this, right? If you have a logic like this, and electron are inside, what's going to happen? Circle around, right? Doing nothing. That's for the storage elements. Each of these inverter is 2 transistor. So that's why it's 4 transistor. And then there's an access element that would be a transistor coming in. Oh crap, I should be draw here. Sorry, I cannot draw for some reason. So these are 2 more transistors so that you can access the cell, right? So basically transistor, think of it as a switch. You can turn it on, turn it off, right? Same concept here. You turn the switch on and off to access. And there are 6 transistors. This is basically going to one of the answer, right? In your midterm, which is what do you use transistor for? There's a lot in the processing side, which is what I'm expecting from the answer. Like, hey, you can have more logic, right, for your CPU. But at the same time, you can also use more SRAM, right? Build the bigger SRAM. These are really, really, really fast. So a small SRAM, it would take less than 1 nanosecond to access. So that's around 1 to 4 cycle. Most of the time, your SRAM in the computer is around 4 cycle, right? So it's really fast. Or if you want it to be bigger, maybe 1 to 3 nanoseconds. So that's range from 4 to 10 cycles. Not bad, right? Not bad. 10 to 15 cycles, not bad. DRAM, this is basically what you buy when you talk about the main memory. DRAM is one transistor, one capacitor, a lot cheaper. Why is also that's a lot cheaper? Capacitor here is tiny. It's so small that it traps less than 10 electrons. Right? So we'll talk about this in DRAM. Like, so if I trap only less than 10 electrons, how do I sense those 10 electrons, right? How do I read them? That's a different story. But this is what DRAM consists of. Cheap, one transistor, one capacitor. Gigabytes of DRAM would take between 12 to 50 nanoseconds, not including the queuing part. Right? So if you have so many access to DRAM, you have to queue up. So that could be even further. Think of a checkout line at a department store, right? So let's say that only 2 checkout line each time take 50 nanoseconds. You go there, you buy a lot of things, you have to wait. We'll learn about the range in the DRAM lecture. So why is there sometimes 12? Why is there sometimes 50? And how did DRAM try to make sure it's most of the time it's 12 nanoseconds? But you see the discrepancy, right? DRAM is slow. 50 nanosecond, convert that to clock cycle, close to 200 cycle. 12 nanosecond, convert to a cycle in modern day CPU. That's 30, 40, 50 cycle, a lot, right? And you don't want to wait that long. Your pipeline don't want to stall for that long. It's way too long. And most of the time, the CPU would stall because of memory. Because of memory. A lot of things you learn in the algorithm class applies here as well. So you have the analysis on the compute, how many operations you have to do, and also how much memory do you have to actually access. And also in this course, we're also gonna cover emerging memory technology like 3D stacked DRAM or NVRAM, right? So that we can look forward a little bit and see, okay, what are we gonna get in the future? Well, these days you can get them now. If you buy high-end GPU, they also come with 3D stacked DRAM. If you buy the Intel Optane, you can choose to put NVRAM in there, right? So these are either high bandwidth or high capacity memory. And again, there are multiple technology. So our goal, right, is we want to be greedy, we want everything. So that should always be the goal of every engineer when you want to provide a solution for someone. I want the best of everything while minimizing the cost, right? So we want both fast and large memory. How do we get that? The idea is actually simple. It's actually simple. If you know DRAM is big but slow, SRAM is really small but fast. So now you can have multiple levels of memory, right? You go then search the L1 cache. If you buy a CPU, one of the specifications on the CPU is what's the size of the cache? How many levels of the cache? More than time you say L1, L2. If you buy it 5 years ago, these days L1, L2, and L3. Because we can afford more transistor because the technology is scaling, so we can put L3 there. And then a large DRAM that acts as a main memory. So this is basically the illustration of what's happening. Now you have the core, right? This is lecture 1 to 7. You have the processor. I want the data. The first thing I'm going to do is check the L1 cache. These are really small SRAM. So really small SRAM is really fast. So most of the time, if you make sure your data is in the cache, in the L1 cache in particular, your memory access is going to be really fast, right? And then if it's not there, well, let's go search a bigger room, L2 cache. If it's not there, go and search the main memory, right? I would use this example that, hey, let's say I'm hungry right now. I want to eat some bread, right? What would be the default thing I'm going to check?
Fridge.
Yes, exactly. I'm going to check my fridge. Like, I have food in there. That's your register is right there with you, right? So you go check, hey, is my data here? Okay, if it's not there, what do I do? Oh, screw me. There's no food in the fridge. What do I do? Let's not do the food delivery service yet. But let's say you have to go out and buy food. What would be the first option?
You will go to the market yourself.
Yeah, basically the closest mini mart that you can go, right? That's like, okay, it's one block here, there's a mini mart right there, and I can go and buy food, right? That's your L1 cache. It's really quick. You can go there really quickly, get your food, come back, almost no interruption, right? Let's say the mini mart doesn't have the item you want, right? There's no bread in the mini mart. What do? You would go to supermarket. So that's your L2 cache. And if the supermarket doesn't have the bread, right? Maybe you find bread in basically wherever is like a big bakery or like a factory somewhere. So that's your DRAM. Kind of guarantees the data is there, right? Same concepts apply here. Same concepts apply here, right? The mini mart is going to be smaller than the supermarket. So they're going to be able to stock fewer items. So there's a chance that your bread is not there. The supermarket is bigger. There's a big chance that it's there, but sometimes it's running out of bread. To be honest, for example, like lockdown just happened last year in Thailand. On those days, there's no bread on the shelf at all, right? So sometimes they run out of food. So you have to go to the next big thing, right? Same concept apply for the memory hierarchy, right? You go and search the closest storage location, not there. Okay, I'm gonna search the next one, right? So let's dive into how these things all work. By first, let's talk about how you program. So there are this thing called temporal locality. This is really easy to understand. If I use a variable, there's a high chance I use that variable again. A loop, for example, I do this. For I equals 0, I is less than n, I plus plus. I guarantee that I'm going to have to access the value of I and n all the time, right? Because it has a temporal locality. I use something, it's likely I have to access it again. So the idea is, well, you can keep them in the fast cache, right? If you most workload exhibit this pattern. The other thing is, if you have this program, sometimes you do this. A of I equals, I don't know, I, right? So this is spatial locality in a sense that if I access this element, it's most likely that I'm going to access something nearby. Spatial is space, temporal is time. So the way I would remember this, temporal locality, time. I'm going to access it again in the future. Spatial means I access these elements, I'm going to access something close by. Okay. And every single program would most of the time have this behavior, right? And we're going to use this behavior to figure out how do I manage the data in the cache. But when you talk about the hardware, there are multiple ways you can manage the data in the cache, right? You can go full-blown software managed cache. For example, the GPU give you this option that, hey, if you know what you're doing and you know this part of the data is going to be accessed by every person that uses the GPU, put that in the cache. You can definitely do that. Many of the data center, that's why I'm going to tie in, right? That's why I'm going to tie in like cluster computing, data center, and things like that as well. They use cache as well, right? Imagine Facebook or Google, let's say Google, right? When you search for a data, where is that data located? It's going to be some data center in the world, right? But the way they optimize the speed, right? The way they optimize the speed is they're going to try to figure out from your location, right? So right now you're in Pakistan, right? So they're going to try to, whenever it detects that, hey, this thing gets searched often from people inside Pakistan, right? So they're going to put the data much closer physically to the data center nearby Pakistan, or even if they have one inside, it's going to be in there, right? So that when you search, it's going to be faster. That's caching as well. And this is software managed caching, right? That's how most cloud providers have to manage their data They have multiple replication, and also make sure the data would be put as close to the user as possible so that it's fast. Otherwise, it's going to take much longer if every time you search for something, it has to get your data from, I don't know, England or like the US, right? It go across the continent. That's going to take a much longer time. But in the hardware, in the CPU, you don't want to do this all the time because this is going to be painful for your program. Every single piece of data, you don't want to manually manage them. So in your hardware, we do this automatic management of data. Hardware would manage the data across all levels. And the programmer only has to deal with memory references. If you program in C before, pointers, right? You just only have to figure out, okay, these are the addresses that I want to access. But if you know the hardware and how they manage the cache, this can actually make your program way faster by making sure your program always hit in the lower level cache. You can always find data there. You can imagine if I am hungry and want food, and then somehow I have the government has a way to manage the mini-mart and the supermarket stocking policy such that every single citizen can always go to the mini-mart and they'll find food. It's going to take much faster time to get food, right? So this is basically what the hardware do. And now we're going to go into the concept of caching, which is basically essentially what we are trying to get as that goal of making sure all the data are in this lower level cache, right? So before we begin, let me kind of define basic terminology. So for the basic terminology, I'm going to make sure you recall the load instruction first, right? What is the size of the load and store? A byte, a couple of bytes, or one data word, right? One data word can be 4 bytes or 8 bytes depending on the machine. A cache also has its own unit of data. We call this a cache block. They are bigger than one load. It's just how this is organized in order. So basically this is done to take advantage of the spatial locality. But why is that the case? If I bring in something, right? If I bring in something into my cache, I bring the entire cache block. Even though I'm just accessing 1 byte, I'm going to bring in the entire thing. So the benefit of that is I'm likely to access something nearby, right? So it should be already in the cache. So this cache block, the size of them typically are designed so that you can take advantage of spatial locality and get more cache hit. The cache block is mapped to some location of the cache. This is basically to help searching. You don't want to search every single byte in the cache. You want to make sure you have a mechanism to go and look up quickly, is my data there? The access again to the certain part of the cache block, right? So when you want to look up the data, there are 2 cases that can happen. You can have a cache hit, data is in the cache. Or cache miss, data is not in the cache. All right, now I'm going to start to have a discussion on design choices, right? The first thing you have to think about is, hey, I have a lot of things that want to access data. The program wants to access data because the program is in the main memory. The data itself, data load, data store, also want to use the cache, right? Once we are going through virtual memory, they might benefit from caching as well, right? In your computer, there's a structure for instruction called the instruction cache. There's also the structure for the data called the data cache. And there's a structure for the translation. This is called the TLB, translation look aside buffer. You might have seen this from the talk last week, right? So those are caching for your translation. The other issue is, well, I know there's a cache. How do I place data in the cache? How do I place the data such that it maximize the number of cache hit, right? If it's full, which one do I kick out? If I need to replace something, how do I pick which one to go? How do you deal with writes? If there are many core that try to access the same cache and different caches, and there are many layers of the cache. So we're going to cover this later. right? Not in this lecture. I think lecture 14, when we talk about multi-core and multi-processor. There's also granularity of management. How big should the cache block be? Should it be small? Should it be big? So a primitive cache design would consist of two main elements. There's a tag store, right? The tag store basically store every information that was related to the cache block. You store, hey, what are the tags? Is my data there? The address associated with the tag, right? These are used to tell whether your data is there or not. And there's also the data store, right? Data store is where you store data. So this would be self-explanatory. If there's no data store, the cache can be pretty much, well, it can be useful in some cases. There's some structure that has just the text store, but you want to store data there. So the primitive cache design would have the data store. And basically what happened is an address, right? An address is used to index and search in the text store in order to get the data in my data store. To check, hey, is my data there? If it's there, where's the data? Can you get that? So now let's go through each of this structure. What's in the text store? Obviously, our old friend, valid bit. If it's 0, don't use that. It's junk data, it's uninitialized. If it's 1, hey, this is valid data, please use them. A tag, this is basically like your name, right? If I want to find someone, I would use the name to find, hey, are you this person? Are you Mohammed, right? So in this case, that's the tag. That's the tag, right? Think of this as a way to search for the correct data. Otherwise, there's no way you can tell if data is correct or not. There's also replacement policy bit. We'll talk about this in a bit. These are additional information that I can use to figure out if this is full, which one do I kick out? It helps in trying to figure out which one do I kick out. Again, there's another thing that inside the text store, and we'll talk about this in a bit. Dirty bits. Dirty bit is when I modify the data. You remember this L1 cache, L2 cache, and DRAM. If I modify something in L1, how can we make sure that same address is updated whenever someone wants to access L2 and DRAM? We use the dirty bit for that, right? So we'll go through this one by one. And we first have to talk about the cache organization, right? We have, say, 4 megabytes of cache is a block of memory. Now we have to figure out how do I search for my data? What's the easiest way that I can use to search for my data? So the cache contains multiple cache blocks, right? 4 megabytes of data, 64-byte cache block. It means, well, I do 4 megabytes divided by 64. There are that many cache blocks in your cache. So each block would belong to one of the cache set, right? And each memory address is going to be mapped to a certain set. So I'm going to draw the figure to visualize this. Here is, let's say I have the cache that fit 16 cache block. And I say there are 8 set. In that case, if there are 8 set, 16 cache blocks, it means that each set would have 2 blocks. You treat cache set as a mathematical set as well, but it has to have this strictly number of cache block in a set. Every single address that you access, let's say you want to access an address that mapped to set number 3. If the address mapped to set number 3 is guaranteed from the address that it would always be in set number 3. If it's not in set number 3, it's not in this cache. This is how you quickly search, right? Imagine like a high school classroom setting, right? In one year, there are going to be multiple classes, right? And let's say you want to search for students. And I would assume the student would map to one of the classroom. It may classroom number 1, classroom number 2, classroom number 3. I have the name of the student. That's my tag. I also, from the address, I have the name. I also have the class number that student belong to. So if you want to search for a student, what do? Do you search every classroom? No, right? Because you know that, hey, student A is going to be in classroom number 3 from the address. So you don't search every room. You go to room number 3 and say, hey, where's the student? I'll use the tag to search inside set number 3. Same concept apply for the cache, right? So with this, right, let me go through some example. Let's say I have the 4 kilobyte cache. And I say 32 bytes is the size of the cache block. Cache block is 32 bytes. Your cache is 4 kilobytes. How many blocks are in this cache? The way I do this is as simple as division, right? 4 kilobytes divided by 32. 4 multiplied by 10 for 24 divided by 32, right? This is 2 to the 5. This is 2 to the 10. So basically this is 2 to the 7, right? So that should be 128 if I don't do the math wrong. Then I say there are 8 sets, right? 8 sets. And now you know that there are 128 cache block, 8 sets. What it means is, well, with this, I also know that each set has how many? 128 over 8, right? Cache block per set, right? And this number is 16, yeah, 16, right? 16 cache block per set. So if you draw the cache, right, this entire thing is 4 kilobytes. This is set, right? Set 0, 1, 2, 3 to set 7, 0 to 7. There are 8 sets, right? Each row is 1 set. And each row, you can divide this into 16 cache block, right? 16 cache block. This is cache block 0, cache block 15 in the set. So that's how it's organized. And when you see the address, you will be able to search from the address, you know the set ID. So you know, hey, it's in set number 2, and then you search, is my cache block there? That process is called a cache lookup. It's called a cache lookup. So an address is divided into multiple sets of bits. There's a region where I have the tag. The tag basically is a name. It tells whether I have my data there or not. It can be someone else's cache block completely. So if the tag is matching, it means your data is not in that set. There's a region called index bit that tells the location of my set. So this is basically, let's say this is your address, right? Your address. This can be 0x, I don't know, beef, right? I'm hungry. Right, let's say the address is 0xBEEF. So you can have the bits corresponding to BEEF, right? So this is F, this is E, this is E, and B is, I think B is 11. Right, so that's your address. A part of this address is going to be used as the index bit. And the top half after the index bit are the tag bit. So this is used to identify if your data is there or not. This is used to identify what set am I going to. Index bit, the number there, in this case 0111 is the set ID. So in this case, let's go to set number 7. It's as simple as that, right? Again, remember this, when we design the hardware, we want simple things. We want them to be simple because we don't want to overload the hardware with a bunch of transistors to do something that can be simplified. You want to make sure everything as simple as possible to minimize the cost. So in this case, yeah, number 7. Okay, go to set number 7. This bit, I would call this byte in cache block. So the cache block is big, right? It can be 32 bits, 64 bits. In this case, it's 32 bits. These bits will tell me which byte in the cache block that I am accessing. In this case, it's 1111, so I'm going to access byte 15 in my cache block. So it's as simple as that, right? You look at this, it seems complicated, a bunch of bits, a bunch of region. It's simple. Look at the size of the cache block. That will tell you the first set of bits that identify which byte am I going? Then you look at the number of set. The index bit will tell me the set ID. The rest go to the tag. Why is that enough for the tag? Why is that enough for the tag? Because with the index bit and the byte in block bit and the tag bit, basically just the tag and the index, it tells you the address of the cache block. There's no way some other address would occupy the cache block because the tag plus the index bit would tell that already, right? So let's actually go dig deeper on how to get the index bit. So each address point to every single unique byte, right? And a cache block is multiple bytes of data. So let's assume that you can go access every single byte here. You definitely, you need log of the cache block size at the lower bit to tell which byte am I going. So in this case, the last n bits is reserved for, hey, what bytes am I accessing? I typically call this byte in block of byte in block bit, just so that I can explain easily. The next m bit is the set ID or the index bits. How can I tell how many bits is needed? You look at the number of set. Log 2 of that is the index bit because you need to convert, right, the number from the binary to the set ID. So if there are 8 sets, you need 3 bits. 9 sets, you need 4 bits. 16 sets, 4 bits again, right? So that's the next 4 bits. And the rest are the tag bits. Right? Simple. So don't panic. If you have the exam that asks about these things, don't panic. It's actually way more simple than the question itself. You go and stop and think about this breakdown because it always go based on this structure. All right, now we know how to access the cache. How about the organization itself? There are multiple ways you can design the cache. Now we are going to talk about the trade-off of having not multiple cache blocks in a set. There are different cache design. The first definition of the cache is called direct map cache. Direct map cache, you can remember this using this basically one sentence. One cache block per set. That's all. That's what the direct map cache is. Every single address is mapped to one location. Only one cache block per set. So when you have a load and store, you use the tag and the index bit. You use the tag and the index bit. If the tag match, it's a cache hit. If the cache doesn't match in that set, no, it's not there. All right? If hit, will return the data. Otherwise, you search the next level. So my question is this: can I write a program that do this? Loop access A, access B. Just access this address A and B. A, B, A, B, A, B. But somehow I get 0% cache hit. Is it possible? Imagine the structure again, hinting, right? Over here is our structure. Cache block 0, cache block 1. This is set 0, set 1, set 2. And most of the time, one thing that can happen, because you only access 2 addresses, right? And let's say A maps to here and B maps to here. What's the outcome? Perfect world, right? Cache hit all the time because A is in the cache block 1 in set 1, B is in set 3. Every time I access A, okay, go to set 1, oh, my data is there. Oh, go to set 3 for B, my data is there. Can I run into an accident where I got 0% hit? And this is where coding becomes important. Like knowing the address can make such an impact because I only access 2 things. So let me ask you this. If both A and B go to the same set but have a different tag, what will happen? Right? Let's say this go to set 1, both of them, but the tag is 20 and 40. It's a different number for the tag. What will happen in this case? So I access B. I first access A, go to set 1. I put A there. Then I access B, go to set 1 again. My data is not there. I kick A out, replace that with B. Then I access A. A is already out, cache miss. I kick B out, put A in there. So you never get a cache hit, right? You never get a cache hit if you have this kind of replacement policy, right? So this is exactly why direct map cache is really fast, easy to build, but you can run into these kind of things. Set associativity is basically introduced to help this. This is basically n cache block per set. N cache block per set, right? The problem with direct map cache is data access can go to the same set over and over, so you never get a cache hit. So the solution, you add more cache block per set by first, you extend the tag store to store multiple tags and extend the data store to store multiple cache block. And cache block is one single unit. So in a set, you can have multiple cache blocks. It will be inside this giant, bigger tag store and data store. Now it contains multiple tags. This is called set associative cache. And when you read the paper, you see something to say 4-way or 8-way cache. Basically, these are number n, right? N-way means that there are n cache block per set. So 4-way means one set has 4 cache blocks. 8-way means in one cache block there are 8 in one cache set there are 8 cache block. And that's how I would remember it, right? It's really simple. N-way means there are 4 cache block, n cache block per set. What is the downside here? Downside is now you have multiple tags you have to search when you look up. Is my tag here? Is my tag here? Is my tag here? Is my tag here? It requires what? Comparator. Remember our exam question about, hey, I have a bunch of tags. How many comparator you required to compare all these things? Comparator are actually hardware component, right? Logic gates. So you basically now have to figure out, okay, how many comparator do I have to add to support this? Right? So set associativity is a great way to allow more cache hits, but also cost more hardware. And then you can go to the extreme, one set, every cache block is there. So you do a full search on the entire cache. This is called fully associative cache. A cache block can be placed anywhere, and you need to do a lot of search in the tag store. It actually does work well if you want to make sure things doesn't get replaced because of the earlier reason they map to the same set. So this can work really well. But if you want speed, this is likely not a good idea. So it might not work as a lower level cache, but a higher level cache, it might be okay. Depends on the design, right? If the cache is too big, it's also not okay because there are tons and tons and tons of cache block. So you might need to find a way to figure out how do I manage this fully associative cache. It's not impossible, but you need additional design on how to actually make it work, right? So that's kind of like the wrap of how cache is managed, right? How cache is managed. Before I transition into how do I put data in or kick something out, I think this is about a good time for a break now that we are 1 hour in so that you can absorb this whole thing. So let's do a 10 minutes break. We'll resume at 10:10. Is that okay?
Yes.
Okay, so let's do a quick break. I'm gonna go get some more water, and I'll be back at 10:10. All right.
All right.
Okay, thank you, and I'll see you in 10 minutes.
All right.
And once you're back, we'll resume and talk about what happened in insertion and replacement.
All right.
All right, give me 1 minute to like devour my food.
Yes, yes, sure.
Sorry. Okay, so let's continue. All right. So the next set of issues is essentially how do I put things in, right? And when it's full, how do I kick something out? Because this can impact performance. If you kick out the wrong way, it can basically make a cache has almost no hit rate. So one of the design that's easy to figure out is direct map. Direct map is easy. One cache block per set. So if I have a new item in, I kick that thing out. But when you have a set associated cache, you basically ended up with a choice, right? A choice of what should be removed from my set. And here are the key issues that you have to design. These are design issues that you can, as a hardware architect, you have a choice of what do we do. Right? Insertion. What do we do if you just insert something new into the cache? Promotion is when you have data access. It doesn't really insert anything new because you have a cache hit. Do you do something with that block? Do you promote them into have, hey, I just accessed this cache. Maybe I just accessed this cache block. Maybe I should have higher priority because maybe of the temporal locality, right? The last thing is eviction. If you want to replace something, you have a bunch of choices. So what do you do? The last bullet point is what I'm going to start with the next slide, which is what we call cache replacement policy, right? When the cache is full, you need to find out what block to be removed, right? And this is called the cache replacement policy. And what might be a good idea? What might be a good policy for us to try? Like, can you think of some policy that would be useful?
The data block that is accessed for that is not accessed for a very long time. Like
Yeah,
this.
so something like I haven't accessed it for a long time. Like the last time I used is further away, right? So that's called the least recently used. Least recently used LRU. That's like one of the most common policy that you can apply to cache replacement. And it actually does make a lot of sense, right? Other design choices are, I want to make it cheap, random policy, I pick something, right? First in, first out. Least recently used, not most recently used. Basically, I would make sure I mark the cache block that I just used, and I don't care about everything else. I would kick something that's not most recently used. Least frequently used. This is more like the frequency of reuse kind of based policy. Or if you can somehow predict the future, not likely to be used again, right? Not likely to be used again. Or hybrid policy, right? So there's, in some sense, there's no optimal policy that's implementable, right? So let's go through some of these design. The first one is basically what you answered, the least recently used based policy. This is actually take advantage of both temporal and spatial locality, right? The cache that haven't been used for a while are not likely to be accessed again. So the benefit is this is actually should be extremely effective, right? It should be extremely effective. But the downside is about the hardware cost, right? Because if you want to have least recently used, what does it mean for a way to detect which block is that? What algorithm do you have to implement in hardware?
Yes, like first in, first out, as you have mentioned.
So basically, you need to be able to sort in some sense, right? And every time you have new access, you have to update the sort order, right? Which is not easy. I mean, it's easy to implement this in software, but imagine you have to implement this using AND and OR gate. It can be pretty complicated, right? And complicated in the sense that it will make the cost going up too high, or in some cases, now your cache is going to be slow because you have to basically wait for this logic to finish computation, right? So there's a large body of work that try to basically approximate this policy, right? Approximate this policy. And one policy that works pretty well in terms of the cost is not most recently used, right? As long as I randomly kick something that I didn't just use, I should hopefully be good, right? And to make it a little bit better, you can do a hierarchical design in the sense that let's say you have let's do four-way, right? Let's do four-way. 4 cache block. Cache block 0, cache block 1, cache block 2, and cache block 3. And let's say you just access cache block 2. Let's say you just access cache block 2. You would then mark this region as you just recently accessed. And then you also mark this pair of region is I just recently accessed this region. So our policy would make sure I protect that. So it would go check these not most recently used region, basically cache block 0 and 1, and check, hey, between cache block 0 and cache block 1, which one was the most recently used between the two? So over here, you need 2 bits, 1 bit for each pair and 1 bit for each region, right? The region that's the most recently used and the pair that's the most recently used, and you make sure you protect that. So in this case, maybe this is the least recently used. Now, instead of sorting, you just need bits and look up which one is not set, which one is reset. So this is actually a lot more simpler, right? But now it would approximate the LRU policy. And it works pretty well, actually, with this hierarchical design. So you can do 2 levels, 3 levels, 2 bits, 3 bits, 4 bits, right? Each time you kind of cover log 2 of the cache block, right? It might not give you the true LRU, but it would give you really good approximation of that true LRU, right? And even with the LRU policy, you can still run into the problem similar to the rec map cache, but we call this set trashing. Set trashing, as the name suggests, we trash things in the set. What does trashing mean? You kind of make a mess, right, of that set. So let me give you this example. What will happen if there are too many data mapped to the same set? And by giving example, I say, hey, I have a 4-way cache, which means I have 4 cache blocks per set, right? And the way I access the cache is this. I access address A, then B, then C, then D, then E, and go back to A again in a loop. A, B, C, D, E, A, B, C, D, E, A, B, C, D, E. Let's assume they go to the same set, but have a different tag, which means they are its own cache block. Different tags, but the same set ID, right? So here's the cache. I have 4 items in there, right? I can only contain 4 cache blocks. When I access A, I put A in there. I access B, I put B in there. I access C, I put C in there. I access D, I put D in there. And then I access E. What happened here? Which one do I kick out because of the LRU policy?
I think A should be kicked out.
Yeah, A should be taken out. E would replace this, right? Then the next access is what? It's going to be A, right? Because A, I do A, B, C, D, E, A, B, C, D, E. So I access A again. A comes in. The last one that I the least recently used one was B, right? So I'm going to kick B out, replace it with A. And then the next access is B. B is not here, so I'm going to kick C out, replace it with B, and so on and so forth. So in this case, you never get a hit. You never get a hit. And one of the observations by one of the paper is that, hey, in this case, right, a random policy can be even more effective here. Just pick things at random, and hopefully, because you have only 5 things, hopefully you get better than 50% hit rate, which is way better than 0%, right? And this is why in some proposal we say, hey, maybe we can use a hybrid policy. The key idea here is to use what we call set sampling. Set sampling is something like this. So let's say I have the cache, right? Set 0 to set set 128. Let's say I have 128 cache set. This is normal because cache is big, right? It can be multiple kilobytes of cache. If the cache block is 64 and there are 4 or 8 cache blocks per set, you're gonna end up with tons and tons of set, right? And you say, hey, I'm gonna sample. I'm gonna make sure some of these sets, like maybe set 1, set 5, set 20, and 21, 22, they use LRU. And then the other group of set, I'll use a random policy. Maybe there'll be 10 sets in total for each, right? And then you sample that. You sample that. And see which one is better. For the one that's better, in that whole period, before you sample again, everything else would follow the better policy. Right? So you can sample this and use a hybrid policy as well, right? Another thing that has to be brought up is this is basically true for every caching, including software cache in data center and everything, is this policy called Belides optimal. Belides optimal is more like a theoretical proof that this is the best policy if we can somehow have black magic and predict the future, right? If you can predict the future, you want to evict the block that's going to be referenced the furthest by the program, whatever that block is. But most of the time, this is impossible to implement. But it's not impossible to simulate. So when you want to design a cache, or when you want to design a caching policy, one of the things that sometimes we do is we compare to Belides optimal and see how close we are to optimal case. So we can simulate, because when you do simulation, you know, hey, these are the program I'm going to access. So this block is going to be accessed last, right? So that's one thing you can do. The next question is, if you keep optimizing the cache, does this also minimize execution time? Yes and no. Yes and no, because cache, as you see, is a part of the memory hierarchy. You have DRAM, you have the core, you have even things that we call network on chip, which connects a bunch of cache and memory together, right? So cache is one component, it's great, and we must optimize them, but it's not every single thing that involved in how the program runs. So when you look about performance, you need to talk about the entire system. And there are actually quite a few papers that I review, and actually many people review that. Let's say I want to propose something in the network, in certain component of the cache, for example, right? And I provide results that say, hey, cache performance is really great. It's a totally valid reason to reject the paper if I say that, hey, I know the cache performance improved, but what about the actual program performance, like system performance, right? So that's why you have to also think about, okay, this is great. What else can I do to make it faster, right? Or what else can I do to make it cheaper, right? So you need to also think about the overall picture on top of this like zoom in picture. All right, so we're done with the replacement policy. If you're curious, there's also a bunch of paper in the reading list that has to do with replacement, insertion on both the CPU side. I also have a paper on the GPU side of things and how do we replace, how do we insert. On the cache insertion policy, right? So when you insert a new cache block, you can have a choice, right? The new block can be in the most recently used position. So most of the time, this actually is working well. Because I just access it, it's likely that I need to use this data again, right? Because I just access the data. So with temporal locality, it's likely that I need it again. But sometimes you write a program that's like read only once. You write a program that read only once. So sometimes you want to make sure if I don't have a reuse right away, I'm gonna kick it out because it's gonna waste a lot of my cache space, right? So this is also another things you can do. And for example, there's another paper at ISCA 2010 from Intel actually that looks into the cache design for both insertion and replacement. Right. So most of the time, the insertion and the promotion policy, which is basically governed when I access the block again, what do I do? Do I update and put that into the most recently used? Right. And this can be easily done by flipping the bit in the cache block in the tag area. Say, hey, I just used this block. So that those are the replacement policy bits. Those are the replacement policy bits. But you can flip those bits and say, hey, I just recently used this block. And most cache design would be talking about insertion, promotion, and replacement. And the one that's most complicated usually, and the one that kind of make an impact on performance is the replacement policy. Because the replacement policy kind of dictates what do I do and how do I manage the cache. And the insertion and promotion would help, basically it would help how do I determine replacement policy, right? So those are about managing the things that go into the cache. The other element of the cache is if I have the write, what would happen, right? When I have a cache block, what would happen? When you write to a cache block, the data change. Let's say I have the sequence of access. I store A to X, to address X. So A is the data, X is the address. And then you store A prime to X, same address. And then you store A double prime to X, and then you load the address X. The code basically dictates that I need to make sure A double prime is the data getting loaded, right? So let's say what happened if I change the data in my cache. In this case, there are 3 changes, right? You need to make sure that the data is updated, right, all the way through the hierarchy so that if someone wants to get the address X, they see the most updated version of the data. So one thing you can do is called the write-through policy, right? There are two, there are 2 policies. So again, let me write store A to X, and then store A prime to X, and then store A double prime to X, and then you load X, right? There are 2 policies. You can do a write-through cache policy. Write-through means whenever I update, for example, A prime to X, I update every single level. L2 have A prime, L3 have A prime, DRAM has A prime. So this is simple. Everything is going to be up to date. Right? Everything will be up to date. All the single level will be up to date. The problem with this is because you don't see anyone using X until the load, right? So this is basically wasting the bandwidth at DRAM because I write to X, then write to X, and write to X again, and no one used the thing in the middle based on the program runtime, right? It might be in the if-else statement. If you go to the if, you never use X. If you go through the else, you need to use X. So in this case, if you go through the if, you don't even have to propagate right? So write-through policy is simple, but it's bandwidth intensive. Another policy is using that dirty bits in the tag to help, right? Because from this observation, when I load to X, when I do the load to X, where do I check first? I have the memory hierarchy, right? So when I load to X, where do I check first? Am I checking L1 cache, L2 cache, or DRAM?
L1 cache.
Yeah, you check L1 cache, right?
Yes.
So the store to X, what about that? Where do I check first? The store to X. Again, L1 cache, right? So in L1, let's say it's only L1, right? And then L2, and then DRAM. And let's say initially everything has A as the data for X, and you have write to X, L1 will get updated to A prime. And do you need to update L2 and DRAM? No, because if there's a load coming in, they're going to check L1 first. So hey, okay, updated data, I'm good, right? Then the store to X is going to be making L1 having A double prime. No one else even have A prime, right? It's fine. No one cares. If I have a load to X, then I get A double prime from L1 because it's going to hit in the L1. It's going to hit in the L1, right? So these methods, you can save the bandwidth and energy by not committing A double prime to DRAM until you need to. And the only case the load has to go to L2 is when? It has to miss in the L1, right? It means that someone has to kick this block out. It has to mean someone kick the address X out of L1. So the only time you commit this right, commit this right and update the L2 to A double prime is when you have eviction. So when someone kicks this block out, what would happen is you go check the dirty bits. If the dirty bit is 0, it means no one has right to this address. So we don't have to update anything. Everyone has the most updated version of the data. If the dirty bit is 1, then it means that, okay, someone update the data. I need to write to the next level. I need to update L2 to have A double prime. Now that it stay in L2, you don't have to update DRAM. You can keep going until someone update and kick L2 the address X out of L2. And then you look at the dirty bits like, oh, okay, it's 1. So you put it into DRAM and update A double prime, right? One thing before I move on from this topic, so I'm talking about single CPU. When you have multi-core and have shared data, this is a different story because now you can have updated value in A double prime in the L1, and someone has its own version of L1 want to access the share L2. You can have the private cache and share cache. Private is private to the core. Share means every single CPU has access to that. So L2 is not updated, then you're screwed because A double prime is not in L2. There's another mechanism to make sure this is updated. We learned that in multiprocessor in week 13. All right, so save this for week 13. Right now, let's remember with a single core, single processor, you can do the write back policy. And write back policy is basically most of the time this is done. The GPU, for example, sometimes they, a lot of time they do write through. There are actually a paper, I think in 2000, if I'm wrong, like 2012 or 2013, that say write through policy for the GPU actually is performing well than write back, right? Because GPU, well, one of the reasons is GPU also has a lot of bandwidth, right? The bandwidth also dictates performance, so that trade-off there. Right now, it depends on the design. It depends on the design. So handling writes again, on the write miss, you have a choice. Are you gonna put this block in the cache or are you gonna skip it completely? Why is that the case? Why is that the case? Think about the instruction window. If I do a write, do I care about when the write finish? Does it block my progress? It doesn't really block my progress, right? Because if I have a future load coming in, I can check the load store queue and I see the new data. So in the CPU world, right, outside of the CPU world, write can make a lot of impact on performance. But inside the CPU, read is more important because read can have data dependency. Read into the register cause data dependency. So when you have a write miss, you have a choice of, do we allocate a cache block for this writes, or do we assume that, hey, it's a write miss, we don't care. I mean, it can go to DRAM, it's fine, right? So you can allocate on write miss, put that into the cache, because maybe you expect that there's a future load coming in to access the address, or you don't allocate. You don't allocate. Why is no allocation sometimes makes sense? Sometimes you do this initialization, right? For I equals 0, I is less than n, I plus plus, right? And then you do a of I equal, I don't know, I plus 10. This is a tons of writes, right? You're not reading anything. You're writing to a of I. And you use it once and you're done, right? So sometimes you might not want to trash the thing in a cache because of these kind of program. So that's why this is also another design decision that you can figure out. Can you detect that the write are not being reused, right? So that you don't have to allocate the block for them. And again, because of these design decisions, right, there are multiple types of cache misses and a different thing you can do to improve it. The first type is, well, I never seen this address before, so there's no way this thing is in the cache. So this is called compulsory miss. It's a miss that must have, right? It's compulsory. You've seen this for the first time, there's no way that's in the cache, except we do something called prefetching. Prefetching, we are not going to cover as much in this course, right? But the idea is we can hint the hardware, or the hardware can provide hints that say, hey, most of the time, for example, you do A0, A1, A2, A3, A4, right? So you know that you're going in steps. So you know if you access 0, just get the next block as well, right? So you can prefetch, get the things into the cache ahead of time, right? We call this prefetching. This can be useful actually for compulsory miss. A conflict miss is when data are mapped to the same set, right? When data are mapped to the same set, in that case, you need a better management for the data, right? You need a better management for the data. Otherwise, you're going to have set thrashing, which means that even though the cache is not full, you go to the same set again, and you lose performance. The last one is called capacity miss. The cache is too small. So again, you can do better management. Maybe you don't want to allocate everything in the cache or buy a bigger cache. Right? So there are multiple things you can do. And from the software programmer point of view, right? Again, this class, I'm going to teach it also based on what if you just want to write software, but knowing the hardware can help, right? In that case, you can look at the performance of the cache because that can impact the program's performance and avoid these three things, right? So to measure performance, one thing you can do is what's the hit rate? How many times you write a program is hit in the cache? What's the cost of each of the hit or miss? You can have a huge cache, right? But the access time is 10 cycles. So a hit, even a hit, it takes 10 cycles already. And so that might not be a design that makes sense. You might want to put in the L1, right? L1 to make sure if you hit in L1, it's fast. What's the total cost of a load, right? If I need to read the data, what's the average time does it take for me to access that data? This can impact performance. And to improve performance, there are multiple things you can do from the programmer point of view. And also from the hardware point of view. It's like a combined thing, right? You can reduce the miss rate. You can reduce the miss rate. The hardware can increase associativity. There's actually design that physically you have the same like 4-way cache, right? But visually, it's kind of like virtualizing this associativity so that you can have many ways, right? You can have better management of data. There are proposals that say, hey, sometimes the program only needs 2 ways because this is how the program is. And then when you share the CPU with 5 programs, then you have 16-way cache. Maybe you can partition how many ways the program demands so that it fits and it works for every program, right? You can have the better replacement and insertion policy as well. Or you can prefetch, right? You can prefetch. And on the software side, you can make sure things fit in the cache. You can write a for loop that only processes the data that just right fit in the cache. And then you iterate over multiple iterations of that loop so that every time you process the data is fit in the cache. One of the common techniques is called block matrix multiply, right? How many workload requires a matrix multiply? And this is basically where I would like to be honest, this is where I would like to make sure the EPE students in TGS who are like, I don't care about computer, I just want to run MATLAB, right? And at the end of the day, they come back and complain that the program is too slow for the application, not real time. It's like, yeah, of course, not real time. You didn't even try to optimize your program. So obviously, you're going to fail to deliver the performance, right? And that's why knowing how to write code is really, really, really important because these things. Block matrix multiplies. Let's say you have a giant matrix, right? When you do a multiply in a giant matrix, what would happen? Cache miss, right? It's too big. You're gonna run into the capacity miss, right? The cache is too small. So at the end of the day, you go to the memory all the time. And you've seen already how long does it take to go to memory? 50 cycles or more, as opposed to 3 cycles, right? Almost 20 times faster. So one of the techniques that most people do, and this is really common, it's called block matrix multiply. Apparently, matrix multiply can be broken down to smaller subunits. You can do matrix multiply by doing submetrics in submatrix A and submatrix B and make sure that thing fit in the cache. Done, right? Everything would hit in the cache. You can also do transpose on the second matrix. Instead of going column, 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 which again would likely to go to the same set, then you change the column to a row by a transpose. That way you have spatial locality. Because now when it's become row, the array becomes B0, B1, B2, B3, B4, rather than B0, B1000, B2000. Right? Now you have spatial locality, a much better cache hit rate. And doing this alone, one thing I can tell you to try right now, write a matrix multiply with a large matrix. But have a version that do a normal matrix multiply, row multiplied by column. And the other version that do row, and then you transpose the second matrix, row multiplied by row of the second matrix. You'll see the difference. It's actually quite a good speed up, actually, with some simple change like this, right? Now that you know how caching works. You can also reduce the miss latency. You add more cache level. That's why some of the machine has L1, L2, L3, and L4. Sometimes they even use called embedded DRAM. Embedded DRAM is the L4. It's much bigger, also better bandwidth, right? So you can do that. You can prioritize the critical load and store, right? We talk about this when we talk about memory scheduling. Also, a lot of my work also look into this area. Can I identify the load and store that has to be fast and we want to prioritize them? Sub-blocking or better replacement insertion policy again, right? You can reduce the miss latency. You allow multiple cache miss to be done in parallel. There's a structure for that, right? Multiple cache accesses per cycle as well. You can maybe handle 10 accesses at the same time rather than one, right? And to highlight the performance of the cache, right, let's look at a program and let's look at a system actually. L1 take 2 cycle, L2 take 5, DRAM take 25. And I write a program, some algorithm that do 100 loads, right, 100 loads. And this program has a L1 hit rate of 80, L2 hit rate of 80. How many cycles does it take, right? So let me do this example quickly, right? So you have 100 load. Right? For the L1, all 100 goes there. Each one of them takes 2 cycles, right? How many are hitting? 80% are hit. 80 hit, 20 miss. So it means that the other 20 have to go to L2, and that will take 5 more cycles. 80% again, so 16 hit, 4 miss. So the 4 have to go to DRAM that take 25 cycles. So in total, 200 plus 100 plus 100. So you spend 400 cycle, right? So you can spend 400 cycle. If these loads were to be add or multiply in the perfect pipelining world, this is 100 cycle. Right? It's a lot faster if it's not a load. So now you see one of the importance of number of loads can impact performance. So let's say you change the program, the algorithm, and you say, hey, I want to make sure it's hitting the cache all the time. But by accident, instead of 100 loads, you issue 1,000. This is what's going to happen. While 1,000 of them would go to L1, that would take by L1 access alone, that's 2,000 cycle, right? 99% hit, which means that 10 go to L2, right? So it's 50 cycle in L2, and then 80% again. So 2 of them, well, 4 of them go to DRAM. So that's 4 multiplied by 25. That's 100 cycle, right? So it's 2150 cycle already just to do this, right? And this is where the problem comes in because I cannot do multiply. Sorry. 80%. Okay, I'm done. 80% of 10 is 2, so 2 of them go to DRAM, so that if you go back and watch the video, it's like, why is it 4? 2 of them go to DRAM, so that's 50 cycle. 80% of 10 is 2. So that's 2100 cycle, right? Way worse because you have many more loads, even though most of the load hit in the L1, right? So most of the time when you optimize the program, maybe you issue the same number of loads, but now the L1 hits much more often. In a real system, most of the time, if you look at the hit rate, you're walking between 80 to 100%, depending on how you write the program. And the other program, I issue 10 load, but it has really crap L1 and L2 hit rate. But the same algorithm, I optimize it so that I don't have to go to the main memory. By some magic. I don't know how that's happened. Basically, this would be 20 cycle. 10 of them go to L2, so 10 multiplied by 50, right? Oh, not 10. 5 of them. Again, I cannot do maths. So for 10 accesses, 50% go to L2, so 5 go to L2. And for all those 5 loads, you have a hit rate of 40, so 3 more go to L3, so that's 25, right? So if you do this, it's 20 plus 25 plus 75, that's 120 cycle for the 10 loads, right? Each load takes way more time. So your program for the performance, there are multiple things you should do to optimize the program. Reduce the miss rate. When looping over a large range of data, see if you can break the loop into a smaller size. Right? For example, can you break the loop such that each time you go through this big loop is fit in the cache? If you have a row multiplied by a column in a 2D array, can you transpose them to make sure it's row multiplied by row so you get spatial locality? And remember that one cache block is multiple words. So when you access data byte by byte by byte, it's gonna hit in the same cache block. So that's good. But if you go word by word by word, check the address. Check the address. Try to make sure they don't go to the same set. Because if they go to the same set, what are you gonna have is set thrashing. You have 128 sets. It's apparently everyone use set ID 0. You have 128 set, you didn't use any of the rest, you go to set 0. It's as if you have one set 4 blocks, right? So this is one thing you need to be aware of. You can reduce the number of memory access from the example I show you, right? Change the algorithm in a way that it doesn't go to memory as much can make a good impact on performance, both positive and negatively, depending on how you optimize it. Remember, data access is always long. Data access is typically long, much longer than compute, like add and multiply. So that's why, right? So what happened in modern libraries that you use, including things in MATLAB, actually, depending on the implementation, right? So modern libraries can squeeze out a lot of performance by itself if the programmer care to optimize for performance. Some of them would try in high performance computing community, like the group of people who would predict climate, right, and see if there's climate change. And obviously, there's one big climate change and global warming going on that you all see across the globe, right? But these kind of machine and program requires complex operation to model the climate, to model the weather, right? So what they would do is they would squeeze out performance by making sure that everything hit in the cache as much as possible. And you rarely have to go to DRAM, right? How do you do this? You would do divide and conquer so that your data set fit in the cache. You would prefetch the data all the time. If you have compulsory miss, well, you know you're gonna need that data. So there's a Intel x86 instruction that would allow you to prefetch. You say prefetch X, the data at address X would be, the chip would try to prefetch them into the cache. You can issue those prefetch commands. You can remap the data so that you spread them out across all the cache set so that they don't conflict in the same set over and over and over, because cache hit really matter. Cache hit really matter for performance. A lot of application requires a good hit rate. It requires a good hit rate. That's it for the caching part. Any questions before we take another break and we transition into virtual memory?
No, I think nothing for now.
Okay, sure. So yeah, as I said, I try to make the lecture portion like basically building from ground up, right? So hopefully there's not a lot of questions, but if you once the sample exam come out again before the final, if you have questions about caching, we can do a Q&A. So again, I'm gonna have the last lecture as the review session. So make sure now that you see the question first, and you might have some other questions, but it is actually simple. You think about caching, it's actually not bad. You just need to calm down. Like most of the time you panic when you, like people would panic when they see the exam. But if you calm down, like, oh, okay, this won't happen. It's actually not bad. So let's do another 10 minutes break. We'll be back at 11:55. No, that's the end of class. That's 1 hour break. We will be back at 11:05, 11:05, 10 minutes. And I'm going to start to first motivate why virtual memory. And I'm not going to go through all the detail, right? I'm not going to go through all the detail. I'm going to save it for the next lecture because it requires a little bit more time. But I'm going to go through why do we want one and how is it done in like the basic of virtual memory, right? Okay, so let's do a break. We back at 11:05. Okay. All right. Okay, now let's resume and let me motivate why, right, why you might want to use virtual memory. It's actually based on the talk that you saw on Monday, right? You might have realized that many systems basically by default would need virtual memory to virtualize things to make sure that multiple people can use the computer effectively, right? And this is why. This is one of the more fundamental reason why. First, you want unlimited memory. Right? You want unlimited memory. You also want to have the virtual wheel, right, of your own memory, in the sense that think about the case where you have 10 applications running, right? As I said earlier, each one is with its own data, which means there's address tied to the data. Right? Address are tied to the data. So the programmer should not have to worry, right, about where each other process's memory are. Why? What do I mean by that? If I am application A, I want to be just worry about the address that I own. But I don't want to be able, like, I don't want to have to worry that, hey, if I use this address that I own, will eventually someone also occupy the same address by accident because they want to expand the size of the amount of data that they hold, right? Programmers should not have to worry about this unless you work with, say, embedded processor that doesn't even have virtual memory. So I think these are rare. These days are really rare. By default, most system has virtual memory. You also want to have memory protection, right? When you have two applications running in parallel, you want to make sure Microsoft Word cannot see the data in Google Chrome and vice versa, right? You want to make sure it's private to the application unless you intentionally declare that that's a shared variable. And the way you share the data across different programs is different, right? It can be through RPC call, which is what I said on Monday, right? You send the data over to another program, which can be the same device, different devices. You can do RDMA, copy the program data from this location to another location belongs to the other program. But most of the time you require memory protection, right? So what exactly is virtual memory? Each address basically is associated with a location in the physical memory. Basically, every single address you see in the program, every single piece of the data has to be somewhere in the physical address, right? It has to be somewhere in DRAM. But the process has its own view of the memory address. So the location of where the data is in the physical location at the physical address, right? At the physical address. Think of this as my address to my house right now, right? And the virtual address of the data is belonging to the application side. I can say home, which means this address that I'm sitting at, right? So the program only see virtual address. The OS and the hardware would translate, hey, okay, that virtual address means this physical address. That virtual address means this physical address. This is done using the memory management unit on the MMU. Every time you see the word MMU in any context in computer science, most of the time it's memory management unit. It is used to manage your memory. Most of the time it's for translating the virtual address to physical address, right? So the first benefit is each application has their own virtual space. You isolate. Now you isolate how each application has to access data because now every application has its own virtual space, has its own virtual address. You don't have to worry as a programmer about where the physical location is. The OS handle that. The system handle that. The hardware handle that. Decoupling the annoying part, you program using virtual address and it's fine. Right? Another thing is you can have unlimited memory. So this is more like an illusion, right, of unlimited memory. So technically this is limited. So if you don't use some of the data and the memory is full, you kick that out to the hard drive, right? And because the hard drive is slow, so most of the time they stays in the main memory. You don't want to put many things in the hard drive parts. It's called the swap, right? If you look at performance monitor, like when you run top on a MacBook, right? You will see the swap memory that is basically holding this data that you're rarely using and your memory is full. So virtual address can be mapped to this much bigger space using what we call the page table structure. Page table structure, as well as the demand paging mechanism, which will look into, hey, where's this page in the hard drive so I can get it back. And one page is typically 4 kilobytes, but it can be much, much larger, depending on what you do and how you would manage this. And the page table structure is basically a tree, right? It's a tree that contains, basically it's like tree. What does the tree contain? It has a pointer to the next node. It then has a pointer to the next node, and then has a pointer to the next node. It points to the next node until you reach at the end, right? That's a tree data. Are you familiar with the tree data structure?
Yes.
Okay, yeah. So it behaves like that. You start from the root. That's page table level 1, and you go. The root would have the pointer based on the address. It would have the pointer to the next level. Next level would have be multiple table, multiple node. Again, there'll be a pointer to the next level and the next level until you add the leaf. When you add the leaf, you have the way to combine things together so you get the physical address, right? And these page table are in the main memory. So in Intel x86, there are 4 levels of the page table. This is basically Intel chip that you have. The root would point to the first level. So every single virtual address will start from there. There are typically 1,000 entry in the table. So you can spawn 2,000 node in the level. And you can think that he's spawning and spawning and spawning, right? And the number of entry in the table can vary as well, depending on the OS management. OS has full control over how I would manage this, right? OS and the ISA, which is index x86, but you can change the ISA. And then when you have the virtual address, it would be combined with what is in that table so that you point to the second level. And you do the same thing over and over and over and over until you add a leaf. That's when you get the physical address. And this process is called a page walk. This process is called a page walk. So now that I say page table is the main memory, page table is in the main memory. And Intel x86 has 4 levels of the page table, right? It means that if I want to get the physical address, I have to go to memory 4 times, right? So we'll think about this in a bit because that's also slow, right? We want to make it faster. But let's go to some example. Let's assume 2-level page table, and each page table structure contains 1,000 entry. And you have 32-bit address. Basically, your address is 32-bit long. And note that 1,000 entry doesn't mean it take 1,000 kilobytes because each entry contains the data, so it can contain multiple bytes of data. And if I give you random virtual address, how do I get the physical address? So this is how. So this time is 32-bit, right? 32 bits. So you first break it down to 3 different regions if you have 2 levels. The first region, we call this a page directory. It will be used to index whatever number is there would go to the first table in the page table. So down here is the page table. In the textbook, this is called the page directory. But now with modern processor, you have 4 level. You don't call page directory page table anymore. It's level 1, level 2, level 3, level 4. Back in the day, they called the first level the page directory, the second level page table. Same thing, same meaning. It's just a table, right? So the number is used to index. So if the number there is 3, you go to this fourth index that corresponds to PTE number 3. This PTE number 3 would have the pointer that points to the next table. It's basically contains the address of the next table. So you can imagine each one of these entries will point to a different table, right? Some of them might share the same table as well. Then you go and get the second index bit here. Use it, and let's say the number is 4, you go here, this will point to another location. This actually now point to DRAM because that's the last location. So this point to DRAM tells you that, hey, that's your page. That's your page. So this gives you your page. The page is actually called the physical page number. Why this name? Well, it's the number for your physical page in DRAM. Then you take the rest of the bit. That becomes the offset. Why offset? The offset is basically starting from here. There are 4 kilobytes, right? You want to search the byte that you want. So the offset would tell, okay, it's this byte. So you start from here and keep going through until you find this location. So you put the physical page number, you append the page offset. That's your physical memory, right? So next week, I'm going to start through this example again because OPAD is not here. So I want to make sure I cover this part, right? So we'll start again at why virtual memory, but I hope this part kind of motivate why do we want virtual memory in the system. I'm going to do a pause here because the rest of the material is kind of governing virtual memory, and I kind of want to talk about some of the work I've done as well. So that's it for today. I don't think we can do this yet because we only have one of you. I was thinking, how are you with Lab 2?
Yes, I have implemented the multi-cycle approach. I want to ask that, like, if we just fetch and the rest of the instructions are not like implemented, we
Okay.
just only fetch in a cycle. So
Yes.
what will be the output then? Because the lab is constructed in such a way that the process instruction makes the next state equal to the make the current next state equal to the current state. Like so.
You then add more states, basically. There'll be state for the fetch, state for decode, state for execute, state for memory, and state for the final state.
Yes, I have added multiple states in the process instructions, but if we just only fetch in a state, like only the fetch operation is performed,
Right.
so what will be the output then in the code?
When you do process instruction, right?
Yes.
So process instruction, the output care about the next state, which is the final state in the write back. But
Yes.
every time you cycle, now you have to move the fetch to decode to execute to memory to write back. And depending on the stage, you do whatever it has to be done. Execute, for example, do the actual add and multiply.
Yes.
Memory, then that's where you access DRAM and update, right? Decode, that's where you figure out is there a data dependency, right? And actually, that's exactly why I'm doing this. Because both of you are working on the projects, right? I'm not sure what to do with Lab 3. Because otherwise, it might be too much work with reviews and the lab and everything, right? But Opad is not here, and he just informed me that last midnight. So I'm basically considering maybe lab 1 and lab 2, and that's it, and then you do the project. And then I'm gonna show you the solution for lab 2.
Right.
Would that be okay?
Yes.
And then I'm not sure what to do with lab 3 yet, right? Because otherwise it might eat into the project time, and I don't want that to be like extra burden with all the reviews and everything you have to do and add other classes as well. So right now, here's my plan. Lab 2 will be due the end of October, so that's 31st, right?
Yes, but in Canvas, lab 2 is
Yeah, basically I was waiting for this vote. because I want to see where things are. And for example, in this case, you haven't done, right? So I would rather have you look through how do I do this? How do I finish this? Then just cut it up and say, hey, that's it. Because data forwarding and pipelining is really important for the conceptual part of this class. So I'd rather have this extension and the rest would be basically for your project, right? And lab 3, I might do extra credit if you want to try, but it's not required, right? So that's a plan. I'm gonna email both you and Opart about this, and let's do a quick vote. Maybe at the end of today. For now, I'm gonna extend the lab 2. If you can somehow finish by today, you get extra credit to make it fair, right? Because original deadline is today. So this is what I'm gonna do. I will first edit. Basically, I'm on the other monitor editing right now. I'm gonna keep the same due date, but I'm gonna change the when this lab would close. So if you do the extension, it would show as late. But that's how I can be aware that whether you want extra credit or not, right? Because if some magical reason you finish by today, you then get extra credit, 10% off the lab 2. So I'll keep the same due date. I'll change the day you can submit to up to October 31st, right? And I'm gonna make that announcement on Canvas, and this is going to be by default. I think I'll get rid of lab 3 for now, because otherwise you're gonna have too little time on your project. I would rather see you focus on the project. Lab 3 will be open after 31st as an extra credit. Basically, it will be open as an extra credit. I'm gonna think about how do I grade that. Basically, we'll do another vote, because I don't want to make it too high value, because otherwise too much for the extra credit. But then again, it's not like zero work, so it is quite a bit of like programming. So we'll see. Yeah. So that's the plan for now. Is that okay for you?
Yes.
You prefer otherwise? Otherwise you go with the same plan. We extend lab 2, but you still have to do lab 3, and I feel like that could be a lot to do in a semester, right? So let's go with that plan. Lab 2 extension is now, I updated it, so it's available until October 31st. If you can submit on time, you get extra credit. Otherwise, you get full credit if everything's correct. And then please think about the project and what to do, because I haven't talked about. So how's the project so far?
I just have understood the Kenny edge algorithm step by step. There are actually 5 steps involved, and I studied that for now.
Okay.
But what I have considered that is I will implement the algorithm like without using any libraries first, and then the second stage will be to optimize that. So for now, I have just understood the Kenny edge algorithm part.
Yeah, that's fine. So that's actually good. So if you have questions, feel free to send me an email. If you get stuck with anything. All right. So let's keep that. Make sure you have the plan for the semester, because I think our semester ends the last week of November. So it's still about 7 weeks from now. It's good to have the plan, because one thing I would need to give you a quick warning, because you take 3 other classes. The seminar should be easy, just respond to the talk, right? But the other 3 classes, they might have projects as well. So I don't want you to be like dying on the last week. So make sure you plan that a little bit. And for the seminar, in a bit, we're gonna transition the speaker to more of the computer side. I'm not sure if you heard about it. So I invite my friend from Google Brain from the US. I'm not sure if it's announced already.
Yes, actually the timeline, all the seminars are enlisted in a document.
So that we like 1 week that if we have the speaker from Google Brain, the other week we have the speaker who are like working in Silicon Valley or tech company in the US, and we do panel discussion, basically focusing on like how it's working there, what's the work-life balance, how do you prepare yourself to actually get there, because most of the people I invited are people who actually like my Thai friends, right? Or friends that I met abroad. But they are basically kind of like from the same background, which is like we are here, how do we get there? So hopefully those are useful, and hopefully they're more useful. Some of the invited speaker, I'm like they're the top of they're wrong. I don't want to say this, but some of them are wrong. Whatever they say. Yeah. And I think I did somehow I think I feel like I'm being a little bit too aggressive as well on questions. But when it's wrong, I don't want you guys to like understand wrong concepts, right? That's like the worst thing you can do in academia. Uh, but yeah. Anyway, so I hope you enjoy the seminar so far. It would be great. I think we're gonna collect feedback. This is like the first semester ever that we've done this. Uh, Most of the goal, right? There are two goals, basically. The first goal is the earlier class of this, like everyone has to take, was called design methodology. And I think that's too much workload on something bullshit that I think it doesn't help you at all, right? The things that you learn in that class is like either common sense or something that you ended up having to look into like a lot of mechanical engineering background, and it's a waste of your time. So we come up with this seminar class. So if you can give us feedback toward the end of the class on how is it so far, and how would you like to structure that in the future? What do you like, and what do you think
Uh,
can be improved? That would be great. Yeah.
Actually, for com students, like we studied power transformers as well in the seminar class. So some topics are rather specific for some fields that
Yeah.
what I think are to be just given to the people who belong to that field.
Yeah. Yeah.
Like the next lecture is now related to yours, like computer
Yeah.
architecture. We will find that interesting, but the power transformer side or some topics are purely related to the power students or the communication students.
Yeah,
Uh,
I totally understand. So that's kind of like a downside of having such a. So if you, well, I guess because this is the end of the class, so let's use this for discussion a little bit too. Like my thought into this, or my take, I guess my take is that because it's like the ECE the program is a little bit covering multiple areas, right? And if you look at a typical ECE program in everywhere else in the world, the EPE students supposed to be able to know how to program. Those are required classes. I'm kind of disappointed that they don't know what the heck is going on with programming at all, right?
yes,
You can't survive in electrical engineering in modern day without knowing how to program. If they don't want to learn how to program, they're gonna die out. That's how I should put it.
yes,
Communication engineering also, like for example, when I took my ECE degree at CMU, I know electrical part. So whatever they say, I understand that. Whatever they say in the communication part, I understand that because I need to took signal system. So those radio signal, it's like I don't know as much, but I understand and appreciate the topic, right? So it's the breadth of knowledge that I really that the my take is that don't just stupidly go deep in one single thing. You need breadth. You need to know more. And one of the downside of a lot of people here at TGGS is once they join a lab, they close themselves off, right? Completely. They don't talk to anyone. And that's a problem because when you actually start working, you realize that somehow you need to know more things. I admit my talk is really technical. so so
yes,
that's true. That's true. And I don't expect them to like know every single detail. Um, it's kind of like a mix of like I kind of want to introduce my lab, right? And what do I do rather than what is this area? Because if you want to know what is this area, you can go Wikipedia, right? It is the same thing, right? And I want to kind of like go into like some of the work that I've done. And these are these are kind of like, so because of the time limit as well, I can't just do everything, right? For example, this class, I spent like 3 hours already on caching, right? And yeah, I definitely know and realize that I'll try to improve the presentation for the next year for sure. But yeah, so it's kind of I think it has to bend both ways, right? I totally understand where it's coming from, but I also need to make sure that, hey, you guys, you're not in the MBA program. You can't just know high level stuff and call it done. You're in the engineering program. You need to know more. I don't want you to graduate and come back, for example, with that 5G speaker, right? He doesn't know anything, right? Whatever he says, like, no, some of them are wrong. Some of them are like, you don't even know what you're talking about, right? That's embarrassing. I don't want our student, because he is also our alumni. And that was embarrassing. If we give a talk somewhere, if we say go to CMU and give a talk, you would die, right? The people there won't do what I did. The question would be like really tough, right? So I want our students to be able to think, right, and learn learn things outside of their comfort zone and at least know what other people are working on. The other benefit of this is like sometimes you realize, oh, okay, that's a new tools that maybe I should look at because it can be beneficial for your whatever your project is doing, right? For example, in your case, right, you might be trying the GPU to run multi-threading, right? That's a totally perfect example of using the breadth of knowledge, right? You're not undergraduate student anymore, and even undergrad students they have requirements. So I'm disappointed in many of the. So I graduate. Let me put it this way, right? It might sound a little bit. Okay, I admit this might sound a little bit egotistic, right? But okay, this is gonna be long, so let me stop recording so that